Johannes Diderik van der Waals was a Dutch physicist that started out his career as a school teacher. He contributed massively to our understanding of thermodynamics and molecular physics. And in this video, we'll be looking at one of his most famous contributions, a way of understanding gases better than we had ever done before. Hi there, I'm Parth and I make fun physics content. If you enjoyed this video, then please hit the thumbs up button, subscribe and hit the bell button too. Let's get into it. Now, before van der Waals came along, physicists had a pretty reasonable understanding of how gases behaved. They knew that gases were made up of atoms or molecules, depending on the type of gas that we were studying, and that these molecules could move around fairly freely and bump into each other, as well as the walls of their container. The problem was that encoding this knowledge into mathematics and then predicting the exact behavior of a gas, which would normally be made up of literally millions of particles, was difficult. For example, if we knew that at a certain point in time the particles were arranged in a certain way, and we also knew the speeds with which they were moving, we could predict what the gas would look like sometime later by using our knowledge of physics, as well as that of momentum and collisions. But doing this for millions of particles was super difficult without computers. In fact, it's even difficult with computers. So instead, physicists work with properties of the whole gas. Things like the total volume it occupied, or the pressure it exerted on the walls of its container, or its temperature, or the amount of gas we were dealing with. And the best simplistic model that they had before van der Waals came along was the ideal gas model. The so-called ideal gas was a way for us to represent real gas behaviors, and it gave us a relationship between the different quantities we discussed a moment ago. The ideal gas model gave us the ideal gas equation, which said that the pressure of the gas, multiplied by its volume, must be equal to the total amount of gas we had in moles, multiplied by the gas's temperature in Kelvin, multiplied by this constant value, called the molar gas constant. Another way to think about this is that the ratio between P times V and N times T was always the same constant for any gas. Or at least it should have been if all gases followed the assumptions that led us to find the relationship in the first place. The problem was with the assumptions that we'd made, because in order to find the ideal gas relationship, physicists had to assume firstly that the atoms or molecules making up the gas were point-like or infinitely small. This is unrealistic because even though gas particles are generally very small, they are not infinitely small. They don't occupy zero space each. They occupy some small amount of space each. And so the ideal gas model worked very well in cases where the molecules were very far separated from each other, which generally happened at high temperatures because the particles had lots of energy and thus would bounce around more and tend to be spread from each other. Another scenario in which this happened was when there weren't many gas molecules in a given volume. So the gas volume was very big relative to the volume occupied by the particles themselves, or the amount of gas that we had. For scenarios like this, we could use the ideal gas equation and get results that describe the gas's properties fairly accurately. The difference between a model ideal gas and the actual real gas were ignorable or negligible. Another slightly wild assumption of the ideal gas model was that the particles making up the gas, atoms or molecules, would not interact with each other. The particles would basically just bounce off. There would be no electromagnetic forces between them. Again, very unrealistic, but the ideal gas model worked fine for cases where the particles only weakly interacted with each other. So, in other words, the ideal gas model described gases really quite accurately in some specific cases. But it didn't work very well for gases at low temperatures, where the particles were close to each other, and therefore the volumes of the individual molecules themselves became relevant. Or if the particles interacted strongly with each other when they came close. Now, if you want to learn more about the ideal gas equation, then check out this video up here, and I'll also link it in the description below. So this is where van der Waals comes into the picture. He made a couple of modifications to the ideal gas equation so that it would more accurately represent more gases in different conditions while still being accurate in the conditions where the ideal gas equation did work. To look at the tweaks that he made, we firstly do a quick bit of rearranging. We'll divide both sides of the ideal gas equation by the number of moles of gas, N. Remember, a mole is just a specific amount of gas, defined by the number of particles that make it up. This way, we can accurately account for the quantity of gas we're studying, as opposed to how much space it occupies. It's a gas after all, it'll expand to fill whatever space we put it in. Now the reason we're dividing both sides by n is so that we can think about the quantity volume per mole. In other words, this is the total volume taken up by the gas divided by the number of moles of gas that we have. So if we put 4 moles of gas in this container, then on average each mole of gas occupies this much volume. The change that van der Waals made was to replace this volume per unit mole with this, volume per unit mole minus some quantity B. This B is a property of the gas that we're studying. It's essentially the volume occupied by 1 mole of the particles of the gas. So let's be very careful here. This is the volume of the container in which the gas is found, meaning this term is the total volume of space occupied by the gas per mole, and this is the total volume of 1 mole of just the particles. Remember, the particles are small, but not infinitely small. They themselves do take up some volume. And hence the updated equation that van der Waals created accounts for the volume between particles by subtracting the volume of the particles from the total volume. Each gas we deal with will have a different value of B depending on how big its particles are. And the bigger the particles, the more space they occupy, meaning they take away from the available volume. Now, moving forward, we can write this term, total volume divided by number of moles, as V subscript m, the molar volume. This is the total volume occupied by 1 mole of gas. And here we're not talking about specifically the gas molecules, but rather the total volume in which you can find the gas. The other change that van der Waals made to the ideal gas equation involved accounting for interactions between particles. Remember how the ideal gas model just assumed that particles only interacted with the walls of the container and not with each other? Well, in reality, particles tend to exert small forces on each other when they get close. Now, if we think about a particle close to the center of the container, then on average it should have all its interactions with other particles cancelling each other out. This is because our particle is surrounded by particles on all sides, and so all of these forces acting on it should balance each other out over a long period of time. However, close to the walls of the container, particles will experience forces that are concentrated on one side. The wall does not exert forces on our particles unless there is a collision between the wall and the particles. But other particles on this side do exert interactive forces even without any collisions between the particles. All of these forces therefore work to almost pull our particles in towards the center of the container a little bit, and therefore reduce the pressure exerted on the walls of the container. This is because there will be slightly fewer collisions between the container walls and the particles, and the collisions that do occur will be weaker due to the inward forces acting on our particles. Now, this whole explanation is very hand-wavy and not quite 100% accurate, but it gives us a good feel for the situation and helps us understand the changes that van der Waals made to account for interparticle interactions. Okay, so roughly how much will the pressure exerted on the container be reduced? Well, the more tightly packed the container is with gas particles, the more particles there will be to attract one of the molecules near the wall. So for a given molecule, the pressure reduction will be proportional to the number of moles of gas per unit volume, N over V, which is the inverse of our friend the molar volume. Basically, more moles of gas in a given volume results in more pressure reduction. So then for a given wall, each molecule would experience a pressure reduction on the order of roughly N over V or 1 over Vm. And the total number of particles hitting that particular wall are also roughly proportional to N over V or 1 over Vm. Because the more tightly packed the container, the more molecules there are to hit a given wall. So hence more molecules to experience a pressure reduction. Therefore, the term that we need to introduce to our equation is roughly proportional to 1 over Vm times 1 over Vm, which therefore becomes 1 over Vm squared. And our proportionality constant we can call A. This A accounts for exact values rather than rough proportionalities, and also accounts for how strong the interactions are between gas particles. After all, each gas will have different strengths of interparticle interaction depending on the actual particles themselves. And hence, the modification we make to the ideal gas equation is we replace our pressure term P with P plus A over Vm squared. Why? Because if our ideal gas equation gives us 300 Pascal as what we expect the pressure to be exerted on the container walls, then the van der Waals equation tells us that maybe only 250 pascals is exerted on the container walls, and the rest is accounted for by the interparticle interactions, the pressure reduction. The van der Waals equation supersedes the ideal gas equation in many cases because it's more accurate in more scenarios. And importantly, in scenarios where the ideal gas equation would work, the van der Waals equation actually reduces to the ideal gas equation. For example, if a certain gas has very weak intermolecular forces and very small molecules, then the values of both A and B would be very small and negligible compared to the terms around them. Therefore, the equation in this case basically becomes the ideal gas equation. Success. As we've seen, van der Waals was a very clever bloke. He used careful reasoning to improve upon an equation that, while often brilliant, would also often be too simplistic to give accurate predictions. He contributed a lot to molecular physics, and I'd love to make more videos about his work. Let me know in the comments which topics you'd like me to cover in the future. And with all of that being said, thanks so much for watching. If you enjoyed this video, then please hit the thumbs up button, subscribe, and hit that bell button for more fun physics content. Check out my merch, linked in the description box below. It features a quantum dice design based on a famous quote from Einstein. And finally, a huge thanks to all my Giga patrons and all the others over on my Patreon page. That's also linked in the description if you'd like to support me on there. Thanks so much for watching, and I'll see you very soon.